Well, good morning. My name is Andreas. Apparently, I'm the oldest person in this room. And I can't stop working because these things are so much fun. We live in really exciting times. We do things we couldn't even dream or imagine before. Okay, so very exciting stuff. My first 2 decades, I was a professor at the University of Colorado, but I worked all the summers for the industry, so I was practical. In the last 20 years, I do consulting for defense and aerospace, especially solving new, unique, and difficult problems for SpaceX, Lockheed Martin, General Dynamics, BAE, practically all defense and aerospace contractors in US and some in Europe, like right here in Germany, Italy, Norway, I mean, all over the place. Because it's fun, I enjoy this stuff, and this is sort of, you can pass the enjoyment to others. We have a 3-day masterclass on these things. That's the only commercial. Because I don't sell software, I don't sell hardware, I don't sell powders or anything else. There are 6 recent enhancements in computational design. I learned the term here. What are they? First, generative design. Say, wow, that topology optimization has been around for 30 years. What's the big deal? It is a big deal because you can do CAD reconstruction with a push of a button. You can do DOE, design of experiments, on the factors we use to tune up, and you need the expert and the PhD guy to do it. You know, like element size, minimum element thickness, spreading, and etc. So you do DOE so you can generate hundreds and hundreds of optimum feasible designs. So the task is, which one do I need after that? And of course, we have manufacturing constraints. We couldn't dream having print orientation direction with 45 degrees 6 years ago, okay? So super exciting. I won't talk about it. Generation of lattice structures. Lattice structures are used in nature for a long time, but nature is a very good designer, okay? It has a lot more experience, failures and etc. But nature is a very good designer and uses lattice structures. We couldn't use them before. 6 years ago, we couldn't even imagine that. Why? Because we couldn't manufacture them. We couldn't even build them in CAD. Now we can. Super exciting, amazing geometries. And also, we have now custom lattices. You can visualize a dream of a lattice unit cell, make it custom, and use it. And the other one, architected materials. Wow. You say, what's a big deal? The big deal is you can get properties for response, like mechanical properties, like stiffness, thermal conductivity, porosity, and etc., which they don't exist in nature. So if they don't exist in nature, how do you get them? Well, it's combination of the materials. So we can get 0 coefficient of thermal expansion. It will be that exciting for the people. They fight thermal stress, you know, stuff like that. Then the next big deal out of the 6 is real-time simulation tools. I'm in the industry for 40 years. I never thought I will be able to do real-time simulation, let's say conjugate heat transfer. Say, what is real time? Oh, you have a big computer. No, they use the GPUs, and they don't use finite elements. They use voxels. So what? Well, now I can do static, model, thermal, CFD, conjugate heat transfer. So big deal. Okay, you can see it fast, but is it accurate? We'll talk about it. Simulation results become features on the model tree. Because it's fast, if I regenerate the model, I can see the pressure drop. So what? Well, if it's feature, I can do sensitivity, I can do optimization, I can do multi-objective design studies, I can do statistical design studies on the fly. I don't need additional software. And if you can do optimization, you don't just do good designs, you do great designs. I won't talk any about these things. If you need this stuff, you take the class. Simulation-driven structures, lattice structures. There are a lot of challenges there. We can generate amazing geometries, so we can grasp the form and the fit. But how about the function? Will it work? Will it break? Will it overheat? Will it vibrate? Will it flow? I don't know. We need to go beyond that looks really good. Is it optimum? Will it work? Does it have the minimum weight? Questions like that. And then, who defines what is the size of a lattice structure? Usually the user says the gyroid thickness is 1 millimeter. Well, there are other options too. You can, based on proximity to surfaces, or any geometry, in NTOP they call them ramps, or you can do even better, have a set of simulation results and say, would you please go to the areas of high stress and make those thicker or thinner appropriately. Then the next big thing is robustness assessment of the uncertainty in 3D printing. Can we do something in the design to overcome the uncertainty in 3D printing? What uncertainty are you talking about? It looks so beautiful. Look at the stuff in the back. Well, look at them closer with a magnifying glass or a microscope and say, oh my God, okay? And finally, manufacturing process simulation. Can I build something? Can I optimize the supports or the setters? If you do binder jet, for example, they droop. They shrink 20%. Can I put a setter part under? We don't have supports in binder jet. But then how do I optimize that without manufacturing process simulation? The TRL level, it's not quite there yet for the manufacturing process simulation, but the useful tools, you should explore them. And also, I want to avoid build failures. I want to build it the first time without cracking at the end and say, oh, what did we miss here? Oh, you have a very thick plate and very thin support. Of course, it will crack there, build failures. And then the other big deal is distortion compensation. We can find out, we can optimize it, but it still distorts, okay? Residual stresses are there. It distorts. What can we do? We want it to be perfect. Design it the other way, okay? Do a compensation on the distortion, so when you print it, it will be straight. Can I capture this back to the model so I can morph my CAD model so when I have one single part, one good source of truth, and say, print that? Okay, we're going to focus only on this talk because we don't have 3 days. On simulation of lattice structures and robustness. What are the challenges in simulating the lattice structure? The first one is massive element size for tetrahedrons, required to capture the details. If I have a unit cell like that, and it has a lot of elements. The other one is interoperability. We have all these beautiful, powerful tools. They can generate TPMS and gyroids and diamonds. And then what we used to do, save it as a step, go to ANSYS, bring the step and solve it. We can save these as steps. Say, what happened? Why? Well, it's totally different geometry. It's implicit or voxel-based, so I can't do that. Ouch. So how do I deal with that? And the other one, can I use my TPMS as a starting point for generative design? Or how can I combine generative design and lattice structures? I'll go a little bit quickly on that, on some of the current solutions. We try to fight the wars with the army we have today, not the army we're going to have 5 years from now. We want the CAD vendors, and some of them listen and they do it, and I'm really excited working with them. We have full geometry representation. So if I have a stupid little bracket like that, and I load it, and I have a little unit cell, and it's about 5,000 elements, okay, I can do it with full geometry, B-rep, a lot of elements, but these FEA solvers are fast. So if I have a single unit cell which looks like that, and I mesh it accurately, I have about 200,000 nodes. 200 for one unit cell. Now, if I have a 10 by 10 by 10, I have 200 million nodes. Totally impractical for realistic problems, which I have several million of those. Okay, if you can see the engine at SpaceX for the Crew Capsule. So the other option we want them, don't give me full geometry representation, give me a simplified representation. Like, let's say, so I can use it for beam and cell elements. So really give me the beginning and end of the beam. Say, how can you design this? You can't even see the intersection. You cannot see the balls and the fillets. It doesn't matter. The human cannot see it, but 3MF can send it to the printer, and the printer knows what to do. And the simulation software understands beams and cell elements. So if I have something like that, and it's a parabolic beam, it breaks it in 3 and makes trapezoidal beam elements and add a mass element of the appropriate size at the center. So if I have something like that, non-uniform sections, I can do trapezoidal beams. So if I have a lattice structure with a bunch of beams like that, I don't do full geometry, I do simplified geometry. So now I have a bunch of beam elements. This shows the coordinate system of a beam element. But the beauty is the user does not need to transfer the nodes and elements. It's automatically transfers beams in the simulation software. So if you look at it closely, you will see beams and solid elements wherever they're interacting. So that's much more reasonable to do. So you can load it and find your deflection, accelerations, velocities if it moves, natural frequencies, but don't expect to find stress concentration at the corner between this and this, okay? Sub-modeling needs to be happen there if you're really interested in that. So you need to understand that, I can capture really the stress level at that corner, but I can use it to do rapid optimization so I can find the optimum lattice structure to generate that desired natural frequency. And if I have 2.5D structures, I want them to become cells. I want to extract automatically the midplane. And that happens today. Whatever I show you today, release software. I'm not paid by any software vendor, so I'm not going to tell you the software tools we use, but you can see the cells and the beams interacting, and it's very easy to do that. Now, he said, yeah, but if you have 1 million cells, even that won't cut it. Yes. Then we use homogenization. Homogenization, we take a unit cell, we squeeze it in all 3 directions, we find the equivalent material properties, and we set up a solid element with these material properties, and we solve for that. Of course, don't expect to find stresses here, okay? But you can find natural frequencies. You can do optimization. Now, let's talk about how do we simulate. Okay, we saw that, but let's say if I have a little heat exchanger for a chip with variable thickness from the top to bottom, if I look at it like that, that's where I put the fan. How do I analyze that? Believe it or not, there's some tools today which they provide you real-time simulation tools. What do you mean real-time? Well, once upon a time, we had 4 viewing modes in a CAD system. Hidden lines removed, shaded with edges. Now we have one more, simulation results. Because the simulation is fast, you can see the results in real time. It takes more to regenerate the CAD geometry than solve it. I'm not kidding. Whoever doesn't believe me, I'll show you. So in real time, you can change, let's say, the size of the unit cell and find a new temperature. Change the diameter of the unit cell and find the temperature. Super exciting stuff. It's really spell checker or Grammarly for design. You do it real time. It's like you have over your head somebody with a, let's make it foam hammer. Every time you make a mistake, bing, oh, you exceed the yield. All right, let's make it back to that, or don't add that hole, and etc. And say, yeah, the structural thermal are easy. I know, I believe you. Also, you can do real-time CFD. How? Well, automatically computes the fluid domain, and it does it. What is the secret? There are two secrets. Don't tell anybody, okay? One uses the GPUs, and the other doesn't use finite elements. It uses voxel-based. And because most of these geometries are voxel-based and implicit, the transfer is very fast. So you can find the velocity distribution and the pressure distribution, and you can cut it in various planes, and you can see this is real-time stuff, okay? I'm not talking to you who need to send it to the cloud and wait for a week and get it back and etc. Real-time on your machine, change viewing mode if you want to see the CAD model. So you can see it in different planes. You can have the unit cell because parametric, you can change anything, and you can see the flow lines. And if you add a little bit extended fluid domains, you can see a better accuracy on the results and say, yeah, but that's too good to be true. There's no way you can have that speed with accuracy. And of course, most of our customers, they fly things in space, so they can take the risk of having a software tool which looks good, but it's not accurate. So we did a comparison for this particular problem. It has 7 million unit cells. You have choice of speed and accuracy. We go always on accuracy because it's that fast. What is between 10 and 20 seconds doesn't matter. So 7 million unit cells for voxels, and 13 million finite elements in Fluent, less than 1% difference. This is super exciting, okay? Because the customers, like the Lockheeds and General Dynamics as well, can you please show me some NAFEMS verification problems? Man, those are simplistic. They're solved by mechanics. They're not practical. Let's do real problems, okay? I had to show a heat exchanger because, you know, that's the one we're printing today, actually, as we speak. So we can very easily find in gyroids, because it's voxel to voxel, the simulation results and find how they behave. And also, you can say, how can you told me of all these things, but how can I combine generative design and lattices? Well, one simple technique we use, we take the initial design domain, we identify the preserved geometry, and we select an appropriate unit cell to use. We don't know which one, but we select one, and we do homogenization, so we try to do generative design with the homogenized material properties, okay? So it's not as strong as steel, it's, let's say, 20%, because it's the homogenized geometry, but I get that. Then the next step is, before you do anything, you go find the stress field. You do a stress analysis, and you find the high stress and the low stress areas, and you save it as a point cloud X, Y, Z von Mises, let's say. But it doesn't need to be von Mises. It can be temperature. It can be a lot of other cool things, which I don't have time to show you now, but take the class. Anyway, and then you say, OK, let me infill the lattice structure based on the simulation results. More dense they are, less dense they are, and etc. I think NTOP introduced that concept a few years back, and a lot of people follow. In summary, the challenges are massive element size and interoperability of TPMS and implicit, and integration between generative design and lattice. How would the solutions are? Have various geometric representations of your lattices, so they're not only for the human eye and visualization, but for the downstream applications like printers, We have structures which the STL doesn't work. We have to bypass STL. So if they're beams, we use 3MF. If they're complex lattice structures, we use CLI, common layer interface files. We slice it in the CAD system and then send it down, or homogenization. In real-time simulation tools, understand voxels and understand implicit geometry. So you can do amazing things with that. And in the generative design, use homogenized material properties and simulation-driven lattices for infill. If I do the same summary graphically, if I have between, let's say, 1,000 and 5,000 unit cells, regular full representation geometry will work great. If I have between 5,000 and 500,000, simplified like beams and cells will work fine. If I have up to 100 million, well, you need homogenization with uncertainty. What the heck is uncertainty? Everything is perfect here. We specify what we want. We'll see that in a few minutes. So typically, the simulation-driven lattices, we have a field, and we can either put more dense field, put more material where you need it, if it's stochastic, and if it's regular, you adjust the thickness here. Some people like N-Top can do both, and some can do either, okay? So this is really exciting because I don't need to specify the user to specify what is the diameter of the lattice. It's the simulation tells you. And here you can combine load cases. So you can say, okay, combine these load cases and give them some weight factor. The other thing, if it's a feature in the model tree, the outcome, in this particular case, you have the pressure drop here. You say, could you please capture the pressure drop or the maximum pressure drop on the surface? And it gives it to you. But because it's a feature on the model tree, you can say, can I plot this is a real problem for a conformal cooling. Conformal cooling, you saw some examples. Yesterday, you have a part and you put a bunch of paths around the path so you can cool it quickly, so you can open up and the next one comes in. But can we get better than that? Yes, we can infill it with lattice structure so we don't have so much pressure drop. And then how do we size the lattice structure? That's one example. We had the target for pressure drop. What is the gyroid unit cell size? You plot gyroid unit cell size here, pressure drop, and say, aha, that's the good one. I'll do this one, okay? So that's about simulating lattice structures. It's super exciting tools to generate. The only thing you need to learn from the first part of the talk, imagination is the limit. For generating lattice structures, use simulation-driven lattices to size it. Now, a few more questions. Can we manufacture accurately these perfectly optimized designs? What do you think? No. Is 3D prone to any defects? They're very difficult to avoid. Yes. How do we apply robustness in design to overcome the uncertainty in manufacturing? What, you want me, the designer, to take care of your problem because you can do something accurately? Yes. And can we design for Six Sigma quality level? The idea is, okay, in the good old times, when money and cost wasn't the issue, you say, okay, go to the minimum possible diameter, the minimum possible thickness, the worst material, and the maximum possible load, and design for it. You over-design, because not all bad things happen at the same time. So we need to introduce statistics and say, I can live with 3 parts per million units failing. Or, I can live with none. So not all bad things happen at the same time. How can I deal with that? Okay, and I searched on the web, by the way, design for Six Sigma quality with CAE, and a freaking paper of mine came the top thing, which I did 25 years ago with Ford Motor Company, okay? So there's not a lot of new things there. These techniques have been out for a long time. How do we deal with them? Well, let's say I have a primitive, a gyroid, and a diamond, and I can plot the aspect ratio versus the volume fraction. So I can have the same volume fraction, so I can find, oh, this is 0.853, this is 0.65, 0.52 millimeters. That's exactly what I want, and that's exactly what I expect. And then you print it. And from far away, it looks good. But then if you look at it a little bit closer, you say, what are these steps here? Well, those are the layers. Okay, and why this is not exactly that? Wait a minute, you mean the printed part, it's not exactly identical to my CAD model? Yeah, it's not. That's the reality. Oh, shh. You say something, oh my God, and you can see how there is difference. And say, oh, this is polymers. Don't worry, let's go to, test it. You test it and you realize that you have different performance. The diamond outperforms the other guys if you test them, in compression. But the real loads is not compression only, okay? You have torsion, you have buckling, you have a lot of stuff. Let's go to metals, man, this plastic stuff. And you go to selective laser lending for 316 stainless steel, and you look at it closely and say, darn, I thought this was a cylinder. What is this roughness here? You tell me I can predict the fatigue if it's a smooth surface and the fatigue depends a lot on the surface roughness, and now this is inside? Oh, you don't want to see it if you're a designer. This is too rough. Or you try to see the porosity if you do, a CT scan, and you see there's a lot more porosity at the joints and there. Oh my gosh, and I was assuming modulus of elasticity, for steel. What is this? You mean this is not uniform inside? It has porosity? Did you, do thermal treatment afterwards? Did you do any hipping? Yes, and it still has that? I said, oh, gee, what am I going to do with this? So if you see another one, you say, oh, all right, I can see for different levels, I can get different roughness on the surface, so I can model this as a sine wave on the unit cell, and I can assume variation based on the period of the sine and the amplitude of the sine. Man, that's too academic, too difficult, because if I change the power, I can get different ones. So that wouldn't work. Wait a minute now. Now you scare me. I have a nice design. I have a fast simulation. I do this. And now you tell me I can't even model the variation and the imperfections? Well, here's what you can do. You can come and do a CT scan on 316L and find the thickness here and the thickness here and the thickness or the diameter here, and you can do a statistical analysis of the thickness, and you can give me the mean and standard deviation of the thicknesses. So what? So now you know that it was 0.99 with standard deviation of 0.01. So what? What can you do? Well, now there is a fear on the designer and engineer, and he asks the question, is my optimized design safe at the presence of variation? That's the question. So he's really nervous now. I optimized the stupid thing. Like what? I'll give you a simple example we use in the class. Let's say if you have a landing gear cylinder, there are two parameters, the radius of the tube and the thickness of the tube. And what we do, we have buckling constraints, stress constraints, and feasibility constraints. Feasibility, the radius needs to be greater than the thickness, okay? If you don't say these things, the optimizer gives you crazy results. But that was, so you draw that line, R equals T. This is the design space, radius, and thickness. We need to understand this concept so we can go to the robustness. Then you can plot the equation for buckling. The buckling load is, P, K, L, E, I. So you solve this equation and you plot it. Everything above the red line won't buckle. Everything below, it will buckle. Then you say, OK, let me print the other line, which is the stress equal to the yield stress times the safety factor, and you have that blue line. So everything below the blue line, it will fail. Everything above the blue line is good. So say, wait a minute, you're taking all my real estate out. I really want 0 thickness and 0 radius, but I can't get there, okay? That will be the optimum because it's, minimum weight. So really, I need to go as close as possible to 0. What is that point? That's what we do in optimization. So really is that point. You say, good. Now I did my due diligence. I had my manufacturing constraint, and the optimization problem was minimize weight, but make sure you don't buckle, you don't yield, and it's manufacturable. So that's the point. Great, so that's the one. Well, if there is variation present, and there is a scatter on loads, material properties, dimensions, and etc., what happened, there is a scatter around that point. So if you design right at the optimum, half of them will fail. So, oh, no, you could say something else. Half of them will fail, and I was on the optimize? What the heck I did all this optimization for? I should go the good old times. We use safety factors, and, we had supply and demand curves, and we try to make sure they're far apart. Yeah, but that's not really optimized. So what do you want me to do here? Well, what I want you to do, shift the optimum a little bit away from the theoretical optimum to account for variation. Man, how do you want me to do that shift? Okay? I'm an automatic guy. I don't like shift. So let's see how we can do that. Okay? It's not that big deal. You have performance requirements, performance targets, upper and lower specification limit. In other words, the safety factor needs to be greater than 1.2. The natural frequency should be more than 200 hertz. The buckling load should be 1.8 times the actual load. Stuff like that, performance targets. And then how I don't know where to start. Well, you identify the parameters, they have variation. Such as what? The loads, the materials, the dimensions, and the range. And we know from a lot of studies that the loads follow log-normal distributions. The materials follow Weibull distributions. And the dimensions follow normal distributions. It took us years at Ford to do that study. But we identify, OK, loads do that. Because you can say I design a car, but would you please avoid potholes? Because otherwise your, lower control arm may fail. If you're in Detroit, you don't have a choice. But, you can do that. So you need to account for variation, for these extremes. But don't penalize yourself to go for the worst case. Then what you do, you set up a design of experiments with these parameters since you know the range. So you have a bunch of variables, and you know the range, so you can do a DOE study. I use one technique called Sobol, but you can use central composite, box Baker, sampling techniques. If you don't know anything, use Monte Carlo. Monte Carlo says, oh, just take a bunch of random points between them. How many? Depends how costly is your simulation. If it's a CFD and takes you 2 days, you will do 4. If it's something real-time simulation, it won't take that much. And then you generate the experiments. So far, I specify the design variables, I do the DOE, generate the experiments, and then I execute a bunch of CAE runs. How many? As I told you, it depends on you take the available time to produce the project, divided by how much is a single run, and you select that many. And then you build a response surface approximation. That's how I call it. Nowadays, they call it machine learning. My dad used to call it curve fitting, okay? So it's all the same thing. Don't be panicking. Oh, my God, machine learning. It's just a response surface approximation. You sprinkle some inputs, you crank it up, and you get some outputs. So that's machine learning, okay? But it's a fancy term now. As I told you, my poor dad had curve fitting with splines, physical splines. You take it and bend it to pass these 2 points and draw the curves. That's the next minimum, all right? But now it's fully automated because we have the power to do that. So if you specify a bunch of inputs and a bunch of outputs, you can generate multivariable response surface approximation. Then you need to check the goodness of the fit because you can be fooled. Is that approximation good? How we do that, I can explain you another time because, we plot the predicted versus computed, and we see if they're around that diagonal. One simple technique. So visually, you can say, OK, that's good. I'm within 3%. After that, it's trivial because you have the mean and standard deviation you measure from the variation. And you can go to Light and Hypercube, make a big sampling, let's say 10,000 random experiments, pass them now through the response surface, which takes no time, and you generate probabilistically the response. So I have now a bunch of numbers for, let's say, stress level. So what? What are you going to do with them? Well, I'll find the mean and standard deviation. And then what I will do, so I'll find the mean and standard deviation of the response variables. And I have down there the targets. So what I'll do, I'll find the sigma quality level, which is really how many standard deviations do I need to move from the mean value to reach my target. And then you find your sigma quality level, and you design for uncertainty. Now, for some of you with their gritty nerds, you can see that, if that's the input, let me annotate. I think I can annotate. If that's the input and that's the output, I can put this in optimization loop so I can find the optimum mean and standard deviation to generate the sigma quality level. That's for the nerds in the audience. I don't do this because they give me a day or two per project like that. So if I go back to this particular example, and I have uncertainty quantification, I can do something simple. I can find the red beams and the yellow beams. What red beams? Well, reds are from 0 slope to about 30-degree slope, and from 30 degrees to 45 degrees, I can call them yellow. Okay? So I have yellow beams and red beams. And what do I do with them? I assign the right mean and standard deviation we measure on the CT scan for the yellow and red beams. So the red beams have wider spread, the yellow beams smaller spread, and the rest of the beams no spread. So now I have the mean and standard deviation of the input, so it will be trivial to do the outputs. So I can have, let's say, for the temperature, I can do the process I showed you before, which, by the way, don't get scared, is fully automated. Fully automated within the freaking good CAD and CAE systems. So if you use, let's say, Creo or NTOP or ANSYS, those things are there. They have different names. They call it Design Explorer or Statistical Design Studies, or I forget, in NTOP they have a block that. So don't be scared. As long as you understand what you need to do, it's not a big deal. It can happen automatically. And you can come down here, and if I can annotate again, you can show, the sigma quality level is 1.6. That's not really good. and you can put the upper and lower specification limits, and you can find out the temperatures and the variations. I think I'm out of time. So I had to show inside the heat exchanger. Okay, everybody shows heat exchanger. This is the one we're printing as we speak with Chelsea. Here is a diamond heat exchanger. It comes in, but there is a misconception. They tell you gyroids and diamonds and TPMS don't need supports. Yes, if you build blocks. But if you undercut them and you have local minima there and there, you bet they need supports. So we put screens because you can't, those heat exchangers are that much, so you can go inside and remove the supports. They're tiny. So we put some screens so you can see a screen there, but you see variable cross-section for the flow, so it will have uniform flow going in. The same thing here, and there is one underneath. There is a nice cone here of supports. So you need to pay attention to support the local minima, and of course a little bit outside. And here it's a beautiful design which has, no matter where you look at it, it's 45 degrees, no supports, because it's 45-degree block like that, and it has inside a lattice with 45 degrees. So, in summary, optimization techniques are great, but robustness evaluation required to provide proof or evidence of quality. Andre will love this, because now that's what he sells. Apply robustness in design to overcome uncertainty in quantification. So we need to oversize a little bit the mean and standard deviation of our parameters to overcome that. In live simulation, what a joy to work with it. It promotes innovation because making simulation experience interactive. You see it real time. If you don't believe me at the break, give me a problem, we'll do it together. It's fun. And a bigger audience can understand that. And here's some AI. For example, in the heat exchanger, if you apply heat on the bottom, you don't need to specify heat transfer coefficient in the rest of the surface. It assumes, okay, I will give you 20 C and 10 watts per meter square Kelvin as heat transfer coefficient if you don't tell me anything. So you apply heat, boom, and you see the temperature. Amazing stuff. This is by ANSYS, by the way. Okay, I don't get paid by them, all right? But it's ANSYS Discovery Live, and it's embedded within CAD systems. And also start thinking a little bit more. What design limitations do you inspire to overcome using these tools? Think of your current design limitations. How can I overcome this? And be daring and bold, because knowledge is power. So if it's so fast to get a response, don't be afraid to say, how about if instead of diamonds, I use IWP? How about instead of beam lattice, I will use 2.5 beam lattice? How about if I make my design weird like that and, you know, whatever? You're not afraid to try a lot of things fast, which accelerates innovation. Thank you very much.